Look at the physical footprint of this facility. Thousands of solar panels stretching to the horizon, supported by dedicated utility buildings and heavy transmission lines. This scale did not exist 2 decades ago. In 2002, Gujarat had exactly 0.16 gigawatts of renewable capacity. Today, that number sits at over 41 gigawatts. The state's 2025 energy policy dictates that by 2030, this installed capacity must more than double, crossing the 100 gigawatt threshold. To put that in perspective, that single state target makes up 16% of India's entire national goal of 500 gigawatts. When that target is hit, 63% of the state grid will rely entirely on renewable sources. Getting there requires a shift in engineering priorities. The primary hurdle is no longer acquiring enough solar panels or wind turbines to generate the raw wattage. The real threat at 100 gigawatts is managing the weight of that unpredictable power. Without strict integration protocols, a grid relying heavily on weather-dependent generation is at severe risk of catastrophic collapse. Standard solar and wind farms operate strictly at the mercy of environmental variables. If the sun goes behind a cloud or the wind dies down, the electrical output drops immediately. This chart shows the resulting duck curve. We see a massive surge of excess power generation during the midday sun, followed by a severe, steep drop-off exactly at sundown, which is precisely when consumer demand hits its evening peak. When your grid consists of 10 or 20% renewables, fossil fuel plants can ramp up to fill that evening gap. But when 63% of your total capacity behaves this erratically, it creates a load balancing crisis that standard grid operators cannot manage. The Gujarat Integrated Renewable Energy Policy 2025 is engineered specifically to solve this physical disconnect. This regulatory framework enforces a structural redesign of the grid, aggressively shifting the industry away from standalone generation to meet the 2030 targets. To force developers to upgrade their architecture, the policy deploys strict legal definitions that penalize older, inefficient deployment models. This graphic shows definition 2.18, which explicitly isolates these older models, labeling them vanilla projects. These are single technology grids connected without battery energy storage and without hybridization. By legally defining what constitutes a basic, unintegrated plant, regulators can separate legacy systems from the new standard they expect developers to meet. The state's mandated alternative is hybridization. This relies on combining the distinct physical profiles of wind and solar generation into a single site. Solar output peaks in the afternoon and disappears at night. Wind generation often picks up in the evening and continues into the early morning hours, creating a natural offset over a 24-hour cycle. The policy classifies retrofitting an existing single-source plant with this second technology as a hybrid Type A project. Conversely, an entirely new facility designed from day one to operate both wind turbines and solar panels simultaneously is categorized as hybrid Type B. Both classifications serve the same mathematical function. They maximize the electrical output fed through a single parcel of land and a single transmission line. Because one source is often generating power while the other is idle, the combined output smooths out the steep peaks and valleys of the traditional duck curve. By legally enforcing these hybrid definitions, the state pushes the burden of stabilizing generation curves onto the developers, well before their power ever reaches the main utility grid. Yet, even the most carefully optimized wind-solar hybrid projects will still experience moments of simultaneous low generation, micro-valleys in output that require active management. This is where battery energy storage systems, or BESS, become the necessary technical bridge. Outlined in definition 2.3, these electrochemical devices are designed to physically absorb excess electricity straight from the generation source during peak production hours. They hold that energy in reserve, only discharging it into the grid when the sun sets and evening consumer demand sharply increases. Look at this stabilized generation chart. The storage system mathematically clips the volatile midday peak and uses that exact stored energy to fill the evening demand valley. This absorb and discharge cycle allows renewable installations to perform the exact function traditionally reserved for expensive, highly polluting fossil fuel peaking plants. The end goal of this integrated storage is to provide round-the-clock, reliable baseline power to the entire state. Definition 2.3 is the specific mechanism that takes unpredictable weather phenomena and converts them into a predictable, dispatchable utility asset. Hardware alone cannot hit a 100 gigawatt target if it gets stuck in an administrative bottleneck. Historically, securing individual grid connectivity approvals has been the primary choke point for deployment. Processing thousands of distinct solar and wind applications through a single-file linear regulatory queue is a mathematical impossibility if the state intends to hit its 2030 deadline. To solve this, the policy introduces a critical legal pathway in Definition 2.5, detailing the roles of the RE project developer and the park developer. This chart outlines how connectivity delegation works. One central park developer acquires a single, massive grid connection. That developer is then authorized to bypass standard red tape and delegate pieces of that connection to dozens of smaller individual projects within their park. This legally shields those individual solar and wind installations from the slow, traditional regulatory approval process by aggregating their paperwork under one pre-approved umbrella. Structuring land rights and grid access this way drastically improves the state's ease of doing business metrics, allowing private capital to deploy hardware faster. To scale to 100 gigawatts, Gujarat had to engineer its bureaucratic and legal pipelines to possess just as much high-capacity throughput as its physical transmission lines. This level of baseload stability de-risks highly advanced deployments that were previously considered unviable. Take agri-photovoltaics, or agri-PV, as detailed in Definition 2.20. This is the simultaneous, highly efficient use of land. Solar arrays generate electricity overhead while preserving the exact same acreage below for active crop cultivation. Scaling up, the policy specifically targets the heavy industrial sector, focusing on attracting capital-intensive green data centers. Server farms require absolute 100% uninterrupted uptime. They cannot tolerate a momentary voltage drop, which means they can only safely operate on a fully realized integrated hybrid storage grid. This stable architecture also allows traditional, highly pollutive sectors like textile manufacturing to completely decarbonize their supply chains without risking factory downtime. Supplying these industries with low-cost, exceptionally reliable green power directly drives down their operating expenses, increasing their cost competitiveness on the global market. By prioritizing grid stability through exact policy measures, renewable energy transitions from an environmental obligation into the primary economic engine for the region. The goal to install 100 gigawatts of capacity by 2030 is massive in its raw physical scope. However, reaching a state where 63% of the grid runs on renewables is physically impossible if developers continue to rely on outdated, single-source deployment methods. That is why this policy is built on three strict pillars: forcing the hybridization of wind and solar, mandating integrated battery storage, and aggressively re-engineering the regulatory approval pipeline. Together, these definitions work in concert to create a robust, climate-resilient power network. The blueprint in Gujarat proves that executing a global clean energy transition will rely just as much on meticulously architected legal definitions as it does on raw infrastructure deployment.